Okay, so this is going to be a presentation on the basics of wind energy technology. And the outline is that we're going to go over a little bit of aerodynamics. Then we're going to talk about wind turbine performance, how to control your wind turbine, and then we're going to get into some CWC specifics. So the first step is, how do wind turbines generate energy? And the type of wind turbines we're generally going to talk about are horizontal axis, like this one on the right. But most of what we're going to talk about applies to vertical axis lifting type wind turbines, like the Darius wind turbines on the left as well. Let's talk about vertical axis wind turbines first. First of all, I'm repeating what I just said. Most of what we're going to talk about and derive does apply to these vertical axis turbines as well. Not all of it. But efficiency, control, pitch angles, maximum limits, all of this sort of thing is similar for vertical axis turbines as it is for horizontal. You can't furl a vot. Furl means to turn it out of the wind to control power. And a vot aerodynamics work differently, which is one of the main reasons we're going to talk about horizontal axis turbine aerodynamics instead. They're easier to understand because they're not time varying in constant winds, where vertical axis wind turbine aerodynamics are. So that's one of the main reasons we're going to talk about HOTS almost exclusively. This talk, however, does not apply to drag-based turbine designs such as the Savonius rotor. This is a Savonius rotor. It's a drag device, and they work really well for things like cup anemometers. They're very inefficient for wind turbines, but they do have their places in some cases. But we're not going to talk about those. First thing I'm going to talk about is airfoils. This is an airfoil, and a characteristic we often describe airfoils by is their chord line. This is the line that connects the leading edge to the trailing edge, regardless of what's going on in between. We then often talk about the free stream flow. That means the flow direction at a distance of infinity away from the airfoil. So far from the airfoil, this is the direction of the flow, not locally. And an important parameter is the angle between them, called the angle of attack. We generally use these airfoils because we want to generate lift, and I want you to be careful here because I want you to note that the lift vector is perpendicular to the free stream flow vector, not to the chord line. That's going to be important later. The vector that's perpendicular to the chord line has a different name. It's not called lift, it's called normal force. So whenever we talk about lift, we're talking about perpendicular to the free stream flow, and that's for reasons of aircraft that are most interested in providing lift to oppose gravity. It doesn't mean as much on a wind turbine, but the convention is still the same. Now, you don't really get something for nothing, so whenever you're generating some lift, you get some drag. And that drag force can be quite small compared to the lift. In fact, the lift force can, in most cases, be between 50 and 80 times bigger than the drag force. But it also is not the case in all cases. So let's talk about airfoil performance specifically. This airfoil on the left is symmetrical, meaning it's the same on the top and the bottom. And for that reason, its lift coefficient, notice the definitions up here, versus angle of attack alpha passes through zero at zero. So it doesn't generate any lift when it's not at an angle of attack. And the lift slope here is fairly linear for a while, and then it curves off suddenly. This is the stall point, and this is a stall region, the area where the airfoil is stalled, where the flow separates. An important thing to note about that is that the coefficient of drag, CD, starts out very, very low and stays pretty low for a while, but suddenly curves up as you approach the stall point, which results in there being a peak point where the lift-to-drag ratio is maximized. And higher than that, when you're generating more and more lift, you can get lower and lower lift-to-drag ratio because the drag is rising faster than the lift is rising. For an airfoil that's more shaped like an airfoil that we would commonly use on wind turbines, which is not symmetrical, you will have some lift at zero angle of attack. That's this point here. But the point I want to make with this slide is that all of this is fixed once you fix your airfoil shape. The shape of the CLCD alpha curve is fixed. It's the airfoil dependent and not dependent on anything else to first order. There are second order effects such as 3D environment, Reynolds number, and so forth, but we'll ignore that for now and just say that once you pick an airfoil, you're basically picking a shape of a CD alpha curve and a CL curve and a CD curve versus angle of attack. So all of this is dependent on angle of attack, and it's fixed with your airfoil. So let's talk about how these airfoils actually work on a horizontal axis wind turbine. And what we're doing here is we're looking at the airfoil as though we're looking at the tip of a blade. And we've cut the airfoil somewhere, maybe at the tip, maybe somewhere else. But we're just looking at the airfoil. I think it's easiest to understand this if you think of this as looking from the top down, and you're looking at the airfoil with the blade pointed straight up. Now we're going to use the same conventions that we did before. This is the chord line, but now we're going to put in the wind. And the way I've drawn it here, the flow from the wind is 90 degrees to the chord line. And that's because we typically run our wind turbines at a pitch angle of about 0 degrees. And a pitch angle of 0 degrees means that the chord line at your reference location is perpendicular to the flow from the wind when there's no wind turbine yaw, when the thing is pointed directly into the wind. So I've drawn the flow from the wind, but that's not the only flow that this airfoil sees. Because this airfoil is rotating, because the blades are spinning, it's also going to see a flow from rotation. And that's coming in from the front. And that flow matters as well. We're going to define something here called lambda, or the tip speed ratio, which is the ratio between these two at the blade tip. It's the ratio between the speed of the flow that's caused by rotation and the speed of the flow caused by the wind. That's going to be important, so this parameter matters, so we're going to define it as a Greek letter lambda, and we're going to keep track of it as we talk. A thing that's important to understand is that these two combine into a single vector that we can call the combined flow, and that combined flow, combined with the chord line, generates the angle of attack that the airfoil sees. This is the same angle of attack that we talked about on the airfoil slide. It's very critical that you understand that this angle of attack is the same angle as the angle between the combined flow and the flow from rotation over here. This angle and this angle are the same angle. And the reason that matters will become clear, but what it means in shorthand is that lambda controls the angle of attack. And we already learned that angle of attack controls the performance of the airfoil. Remember, all of these charts are fixed when you pick an airfoil. Now, this is for a particular pitch angle. If you change your pitch angle, then this angle won't match this angle, but it's still true that lambda drives the angle of attack, and the angle of attack drives the airfoil performance. Now, this combined flow does the same as before, generates lift. Notice that it's perpendicular to the combined flow, not to the chord line, as we discussed before. And again, you can't get something for nothing, so you get some drag. But you can combine these two by putting them tip to tail and create a combined vector that the airfoil is generating. And it's useful to resolve that vector into the plane of rotation so that you're turning these forces that the airfoil is generating into forces that the wind turbine as a whole sees. And one of those forces is thrust. That thrust is how much force the airfoil is generating that's trying to break itself, pull the tower over, rip the foundation out of the ground, and do all kinds of other things that you don't really want to happen. In other words, the thrust generated is not something we really want. What we want is this torque vector. This torque vector is very small, generally much smaller than the thrust vector, but it's the vector that creates all of the energy that a wind turbine will ever produce. All of the energy that's coming from all the wind turbines in the world exists because of this little tiny torque vector. So you would like to ideally optimize your torque while minimizing your thrust. But that's a challenging thing to do, and having to do a lot with detailed design. But this is how a horizontal axis wind turbine works. The combined flow creates a combined vector, which creates a thrust and a torque. So let's talk about rotor efficiency, something we call CWC, or coefficient of power. The power in the wind, of course, is kinetic energy. It's the energy caused by its motion. And we're going to say that the M, the mass, is defined as the amount of air that's going through the rotor in a particular time. So that's the density of the air times the volume, which is the density of the air times the area that the rotor is sweeping out, the circle, the size of the rotor, times the velocity, because for example, in 1 second, if the velocity is 10 meters per second, you'll get 10 meters of motion. So the cylinder of air that went through the rotor is 10 meters tall, and the area in base for that cylinder times the density, and that gives you your mass flow in that 1 second. So the power in the wind, if you just substitute rho AV into this equation where M is 1/2 rho AV times V squared, which is 1/2 rho AV cubed. And this is important because this cube here really matters a lot. When the wind doubles, you get 8 times as much power. And since the wind can be more or less unlimited, you have to deal with the fact that the power that the rotor can generate can be almost unlimited. Rotor efficiency that we're trying to define here, however, is just the power out, however much power your turbine is producing, divided by the power in the wind. So that's how we're going to define CWC, and we're going to use that later to talk about a few things. So the result, just to review, is that constant lambda means constant angle of attack for a given rotor design and a given pitch angle. Constant angle of attack means constant lift to drag ratio and all of the other parameters that the airfoil produces, which means with the same geometry and airfoil performance, CWC is also a constant. So once you fix your geometry, you choose your airfoil and your twist distribution and pick a pitch angle, then CWC is constant with a constant lambda. So what we really want to understand is how CWC varies with lambda. So the CWC versus lambda, or tip-speed ratio characteristic, for your particular rotor design is the crucial thing to understand and to optimize if you want your turbine to perform well and to be controllable. So let's summarize this entire section. Lifting type wind turbines are all similar regardless of configuration, including VOTs. Angle of attack drives airfoil performance. Lift to drag ratio and all of the other airfoil parameters are driven by airfoil shape. Tip speed ratio drives the angle of attack, which combined with all of this other geometry stuff controls turbine performance. And so CP versus lambda is the main thing that you want to understand if you want to understand a wind turbine rotor. So let's look at that. Let's look at a CP lambda characteristic. Okay. So this is an idealized CWC versus lambda. It's not for any particular rotor. And there's a couple of points I'd like to point out on this curve. First of all, there is an optimal, and the optimal occurs at a particular CWC and at a particular lambda. In addition, if you allow the wind turbine rotor to accelerate and tip speed ratio therefore to rise, eventually it will get to a point where it's not generating any power, where CWC is 0. And that point we usually call the runaway point. This runaway point is very important for design because that's where the wind turbine is going to go if you don't load it. If you don't generate any power or you don't have brakes or some other way of loading the rotor, then this is the point where your wind turbine is going to want to operate. And this point can be substantially above the optimal point. In fact, it can be 2 to 3 times the optimal point depending on your rotor design. In this case, it's a little more than 1.5 times our optimal point. But this point can be 16 or more in some rotor design cases. So you're going to need to understand where your runaway point is, your optimal point, and the lambda at which that optimal occurs. C sub P also varies with pitch. The one that I showed on the previous slide is a particular slice of this for a particular pitch angle. But when you vary your pitch angle, you also vary your C sub P curve, your C sub P versus lambda curve. And it's important to note that the optimal point does not stay at a fixed lambda as you change your pitch angle. This peak point can change with tip-speed ratio. For example, down here, the optimal lambda is around 2, whereas up here, it's around 7. If you want to change your C sub P while your tip-speed ratio doesn't change, you can change your blade pitch, and then you'll run down the curve this way. And you can even go negative, so you can slow the rotor down by pitching out in either direction, by pitching until this is negative. The point is that controlling where you are on this surface is how you control your wind turbine. And you can do that by controlling either tip-speed ratio or controlling pitch angle, or both. So we're going to do something we never do in a presentation, and that is we're going to show some equations. Well, you all are students, so you should be able to handle a small amount of algebra. The question is, how do we sit at that optimal point? And we're going to derive that right now because it's fairly simple. First, we're going to start with the definition of power in a shaft, which is torque times speed. And then we're going to write that as the equation. Power is torque times omega, and solve for torque. So torque is power divided by omega, just by dividing through by omega. We have our definition of C sub P from where we derived it on the previous slides. Power out divided by 1/2 rho A V cubed. But now we'd like to solve it for power, this power out. So we'll just multiply by the denominator here and get power is equal to 1/2 rho A V cubed C sub P. This is a fundamental equation for understanding wind turbines. Now we can substitute this equation into this equation by putting this in for power, and by and defining A as pi r squared for the rotor area, where r is the rotor radius. We also have our definition of lambda, tip-speed ratio, of omega r over v that we had from before. And I want to solve that for v and get omega r over lambda. And now we have stuff that we can substitute. We can substitute pi r squared in for A, and we can substitute omega r over lambda in for v and get this equation. This equation is a little bit messy, so we should simplify. So we can expand terms, put the 1/2 down on the bottom, and put the lambda cubed down here. We can expand this term so we can have omega cubed r cubed, but then the two r's can cancel and turn into r to the 5th, and the omega cubed over omega can turn into omega squared, and we get this equation. And if we put the omega squared out front, we notice that all of this stuff is more or less constant. The air density changes slowly with weather fronts and so forth, but for most of the time it's fairly constant. Pi is a constant, our rotor radius is a constant. The C sub P, the optimal C sub P, is a constant if that's where we want to sit. The lambda at which our optimal C sub P occurs is a constant. So what we have is a whole bunch of constants, or nearly constants, multiplied by our turbine rotational speed squared, and that's our torque. So that's our final equation. Torque equals k omega squared, where k is a bunch of constants. Now you can change rho with air density changes in the atmosphere, and you can decide not to run at the optimal point if you want to control your turbine. But for an optimal operation, you'll sit at the constant C sub P at the optimal, a constant lambda wherever that occurs. The air density is going to be relatively slow changing, and your rotor radius better not be changing unless something disastrous happens. And that's how you can control your wind turbine to generate optimal power. Very simple derivation. The question, though, is how high can CP go? Can it be unlimited? This is called the Betz-Lancaster limit. Well, what does the rotor do? It slows the wind down. It extracts kinetic energy from the wind. I'm not going to go through the whole derivation here, but you can define this as the power created is sort of the difference between the velocity going into the rotor and the velocity going out of the rotor with our normal wind turbine stuff out in front, our 1/2 rho A V cubed, where V is the average or the free stream velocity. you can simplify this equation by substituting and putting this 2 with that 2 and getting 1/4. But don't forget, the power in the wind is 1/2 rho AV cubed. Remember, we derived that earlier. Well, if you divide these two and simplify, you can get this equation for C sub P. And that, if you plot it up versus V out over V in, looks like this. Now, you can take the derivative if you want to and solve for when it's 0 and get the peak. But you can also look on this plot and see that the peak occurs at 1/3. When V out over V in is 1/3, you'll get your optimal C sub P. And if you substitute 1/3 into this equation, you'll get that C sub P is 16/27, or 59.26%. This is the ultimate limit for a wind turbine that's extracting kinetic energy from the wind in this way. You cannot beat this, and anybody who claims their wind turbine beats this is violating the laws of physics. This is based on just first principles, and the idea is simple. If you slow the wind down too much, no new wind can come into your rotor. If you don't slow it down enough, you're letting too much energy go through. And in between those two extremes is some optimal point, where you're letting just enough wind go through to let new wind come in, but you're still extracting a lot of that wind energy that's coming in. You can't beat this point. And in reality, it's fairly hard to get close because you have drag on your airfoils, you have a limited speed, and your generation system isn't perfectly efficient. So let's do a summary for our rotor efficiency. We define C sub P. We understand the maximum and why there is a maximum. We learned that CP lambda pitch surface is how you control a wind turbine, and that you can use torque or pitch angle to control where you are on that CP lambda pitch surface to control your turbine. So from now on, let's look at how we might best control a wind turbine. So this torque vector is a plot of torque versus RPM. Remember, our torque was K omega squared. So I'm plotting this versus RPM, or omega, which would be in radians per second, perhaps. But it's just rotor speed, so we can plot that to make this simpler to understand. Now, below some speed, you might have region 1, which is where you just can't generate any power. There's just not enough wind to get the rotor turning fast enough for your generation system to generate any power, to overcome the friction in the bearings and those sorts of things. And that's pre-cut in. At some RPM, you might be able to cut in, and that'll occur at some wind speed. And the competition includes you trying to cut in as low as possible. Then in region 2, you want to generate as much energy as you possibly can. So you use that torque equals K omega squared rule to set up the optimal point, where K is solved for your optimal point. But at some point, the wind will get high enough that you're going to break something if you keep allowing this torque to rise. You're either going to hit a torque limit or you're going to hit a speed limit at some point, and you're going to have to limit what's going on, either the speed or the torque. And there's no rule that says you have to hit your torque limit and your speed limit at the same time. You might hit them at different times. And if that occurs for your particular design, if your torque limit and your speed limit aren't at the same point, then you might have to have some kind of connecting region in between to make this curve continuous. And we usually call that region either region 2.5 or region 2B, something like that. The point is, this is the vector you use to control your wind turbine across these three regions. Now, region 4 is not shown here, but it would be where you have so much wind that you have to cut out. You have to stop the turbine to prevent it from breaking the tower or breaking the foundation or the blades breaking or something like that. And that's called cutout, and that's also part of this year's competition. So let's talk about region 3 a little bit because it's important. Region 3 is crucial because it's where you switch from controlling power to be maximum to controlling them to be specific values at the limits of your design. This is done to limit torque, thrust, and centrifugal loads on the blades. If these are not limited, catastrophic failure can result. I.e., if you let your turbine run away, you can often result in a failure, and we've had failures in our wind tunnel of Collegiate Wind Competition wind turbines from this cause. So on large wind turbines, control of region 3 is often dual fault tolerant. In other words, two separate things can fail, and you can lose the power grid at the same time, and the turbine won't run away. This type of control in Region 3 is so important that it often comes with some kind of a name. We'll often talk about pitch to feather control for power, pitch to stall control, which is uncommon but works very well. Stall control, where you slow the rotor down and allow the blades to stall to control your power production. Furling, where you turn this turbine away from the wind, either sideways or upward, in order to control the power produced at high winds. And that's been common in the past on smaller turbines, though it's getting less common these days. Still is used, though. It's very uncommon on large turbines. But it's so important to do Region 3 well that they actually name wind turbine characteristics after it, like a stall-controlled wind turbine or a pitch-controlled wind turbine. So we're not going to talk about the electrical system in detail here. The point here for you to understand is that you have to turn the power that the generator is into something you can control. And the way that's done on big turbines is you turn it into DC from AC, use an inverter to control how much you're pumping into the grid, and then a transformer transmits it out to the grid. There's lots of ways to do this. You can have different kinds of rectifiers, different kinds of inverters. You can have doubly fed systems. I'm not going to go through this in detail because the point I want to make is that there's lots of ways to design a power electronic system that enable you to do what you want to do, which is to control your torque, the torque that the generator is extracting from the rotor. And you need to design this carefully and think about it carefully because it's one of the two parameters that you can control. You can control torque and you can control pitch as well as the design. And you have to figure out how to do this in a way that enables you to control that torque accurately, quickly, and reliably. So the control system summary, you want to control the torque vector through all your regions. You want to control your rotor speed with torque in Region 2, but understand that you have to control Region 3 differently so that you don't let the rotor run away, generate too much thrust, generate too much centrifugal load, generate too much power for your drivetrain system or whatever. There's lots of ways to do this electrically, and you need to think about that carefully and work it out and get this to work. And now I want to move on to talking about Collegiate Wind Competition specifically. The CWC electrical system, well, the CWC turbines aren't connected to the power grid, which is a really nice thing because you don't have to create that grid-side inverter. And that's a very hard thing to design because the grid is very unforgiving. And so it's a good thing that we don't require it. You only have to design the piece that connects to the generator, and then you get to design your own thing for the other side, your own load. You have to control your generator torque somehow, though, using this system. And there's lots of ways to do that. You have to feed your load, and you have to control the turbine without using the load to do that. Efficiency does matter. Remember, the way the Collegiate Wind Competition works is that we measure the electrical power you're transmitting to the load. And so that's the only power that counts towards getting points. Doesn't matter how much power your rotor's producing. It only matters how much electrical power you're getting out of your system. There are lots of ways to do this, and make sure you enlist help. Some people have gone to the electrical engineering department, enlisted the help of power electrical engineers, and those people have typically done well. This power electronics design is typically a failure point that a lot of teams run across because it's fairly hard to do, and if you don't get help of people who are trained in it, it'll be even harder. It turns out when you're designing wind turbines, especially wind turbine controllers, it's incredibly useful to create a system that allows you to do hardware-in-the-loop simulation. And what do I mean by that? What I mean is you have your controller running where it thinks it's controlling the real wind turbine, but you're giving it simulated inputs. You're controlling the wind in a simulation. You don't have to have a wind tunnel. In fact, you don't even have to have a dynamometer or a drive system. You're just feeding it simulated inputs to make sure that it's responding to those simulated inputs properly. You can also add a dynamometer and make it even better by simulating the wind into the dynamometer. So the dynamometer is controlled to simulate how the rotor would perform, and then you see if your wind turbine controls it properly. And that works even better because it allows you to test your generator, your drivetrain, your power electronics, your load, and your control system all together instead of just the control system. And you can even do this together like I just discussed, where the hardware in the loop simulation is driving the dynamometer's speed to simulate real wind. It's way easier to do this on the bench than it is to constantly have to be in a wind tunnel, which some of you might not even have available. For the Collegiate Wind Competition, this is even better because the dynamometer can be tiny. For large wind turbines, this can be a real pain because the dynamometers can be enormous and cost tens of millions of dollars. For you, they should sit on the table, be the size you can put in a backpack, and cost a couple of $100. So I'm going to give you a suggested design sequence for Suggest at the Collegiate Wind Competition based on our experience of watching teams at the competition. Number one, read the rules. It's very important to understand what the problem is you're trying to solve, or you're not going to be able to solve it properly. Step two is even more important, and that's to read the rules again. Make sure you really understand this, or you'll never be successful. Get a dynamometer built early, and get it under good control so you can use it throughout the competition, and even bring it with you to the competition to test your turbine and make sure everything is working properly. Oops. Build on hardware in the loop simulation using the dyno if possible, and get it done early because you're going to need it to test everything else you build, including the software. Build the turbine drivetrain early and start testing it early on the dynamometer, because it's easier to make modifications than it is to start from scratch. So don't worry too much about designing the perfect device. It's more important to get something working and then improve on it than it is to design the perfect device from the get-go. The power electronics and controls are typically the hardest part. Don't forget to choose a load and get it built and working early as well. People have had the load cause them to fail at the competition as well. You can always change it later if you need to. Again, it's easier to improve a design than to design the optimal design from the get-go. This drivetrain can probably be used even if the rotor design changes. For example, you could change the number of blades, the shape of the blades. You could even change from a hot to a vot with the similar drivetrain if you can control it. Did I mention that it's important to start early? Did I mention that often enough over here? Don't wait till the end to get this going. Get it going early so that you have time to optimize and build all the rest. And by speaking of building all the rest, that's when you start building your rotor and all of the rest of the mechanical parts. This is typically the easiest part of the competition for most of the teams, getting the stuff built. You do have to do it, and it is a job, so you do have to plan for it. But make sure you get this drivetrain done and under control early, and this stuff will fall into place. Make sure you design the controls to avoid wind turbine runaway. Remember, we talked about how disastrous a runaway can be. But also design and test your rotor to handle runaway. That's one of the milestones that you have to do. So this is your redundancy. Design it to avoid runaway and to handle runaway. The way the rotor is manufactured might be crucial. Think about that, especially if you're using 3D printing to build your rotor. And make sure you do that runaway test, but think critically about how you're going to do this, because those blades could end up going really, really fast, and they could end up breaking, which means do it safely. Don't be in the rotor plane or anywhere near it, and do it as though it's going to explode, and be safe in that case. If I were doing this, I would do this outside, a long distance from everybody. But another way to do it inside is to build a sturdy cage around it to contain all the parts. That's effectively the method we use in the wind tunnel, where the entire wind tunnel test section is surrounded by a half-inch of Lexan. Finally, after you get all this done, do some wind-on testing. There are lots of ways to do this. You don't have to have a wind tunnel. But once you do that, you're going to probably find some problems. So go back and do some more hardware in the loop testing, solve your problems, and keep repeating that until you either have the most perfect wind turbine ever built by humankind or you run out of time. And prep all this stuff for travel. Make sure you prep it so that it's not going to get broken in the travel experience, which can be fairly hard on these things. And make sure that you remember what the goals are. Nobody's coming away with this with $1 million contract. Everybody's going to hopefully come away with this with a lot of learning and a lot of fun. Those are the goals. By the way, when you're prepping for travel, make sure you bring your dynamometer if you've built it and still have it working, because it can be used to solve problems. And bring spare parts, and spare parts for your tools, spare tools, that kind of thing. Anything you might need to fix problems when you're here. Finally, our conclusion. We went through and understood how wind turbines work, including understanding why the CP lambda versus pitch surface is so important. We learned how and why to control wind turbines. We learned that the electrical systems are crucial, and there are a lot of different forms, and so you need to spend a lot of time and a lot of effort making sure yours is solid. Gave you a suggested sequence for being successful, and we reminded you repeatedly to read the rules and understand them. I realize they're fairly long, but you can read them all in less than an hour, and it's really important. So that's the end of the talk, and now I'd like to open it up for questions if there are any.